So in this installment, we're going to look at work that's being done at an angle. So we see this gentleman here, this dad, and his daughter in a wagon, and he is pulling her. And the question that we might be asking leading into this is, does it make a difference in terms of what's going on to change this angle? Does it matter if we change that angle? If we're applying that same amount of force, let's say that father can only apply that amount of 50 newtons and he applies at different angles, what effect does it have? And so this is a habit we want to get into, is imagining different conditions. What happens when we change things? What happens when the force is directed this way versus directed this way at 90 degrees? So what we might see is that if we keep increasing this angle, it's going to become harder and harder to pull the daughter. And in fact, when we get to 90 degrees, we won't be able to pull it at all because there's no part of this force that's pulling the cart forward. And so we then see that the work that is being done here, because the work is being done against friction, we have friction acting backward, and we are trying to pull the cart in that direction. We only need enough force, enough applied force, to be equal to the force of friction for it to travel at constant velocity. So why should that be? Well, F net is ma. And if we are traveling at constant velocity, the acceleration is 0, so that would mean the net force would be 0. So to travel at constant velocity, the applied force in the horizontal direction needs to be equal and opposite to the force of friction. But we should then be able to see is that when we are at this particular angle, some of that force is in the vertical direction, Fz, and some of that force is in the horizontal direction, Fx. And when we change the angle, we change that part of the force that is vertical and that part which is horizontal. So ultimately, if we have this situation here that the wagon being drawn at constant velocity. Now, the situation of constant velocity is very important because when the velocity is constant, we know the forces are balanced. And we know a lot that's going on. So in most of these situations, we'll always be talking about a constant velocity. So constant velocity, no acceleration, forces balanced. So how much work does he do over 30 meters? Well, the work is equal to the average force times the distance. And so we know the distance is 30 meters. And so the force, if it were 90 degrees, would be 0. None of that force would be moving it to the right. And if we bring it down to 0 degrees, all of that force would be pulling it to the right. So in our triangle that we have, we know that the hypotenuse is 50 newtons. We have 30-degree angle. We have Fx and Fz, with this being a right angle. With our trigonometry, this is our hypotenuse, this is our adjacent, and this is our opposite, and this is our adjacent angle. So we can then write two trigonometric statements for this. We can write out sine. So sine of theta is opposite over hypotenuse. And so then sine of theta is Fz over 50, and solving for Fz is 50 sine theta, and of course theta is 30. So Fz is 50 sine 30. Now sine 30 is a good number to know, is equal to 0.5, so we have 50 times 0.5 or 25 newtons. And that's one of the reasons we see 30 degrees an awful lot. So we know now this side, the vertical, is 30 newtons. Well, to find the adjacent side, Fx, we have cosine theta is adjacent over hypotenuse, and cosine theta is then Fx over 50, and Fx then is 50 cosine theta, which is 30, and 50 times 0.866 is the decimal equivalent of that,